Okay, dear colleagues, may I have your attention? Please come back. We would like to start with our afternoon session. So I hope you enjoy your lunch and you are ready to listen to our next speaker. Is nice guest, Mr. Vladimír Strunga from Czech Academy of Science, and he will tell you something about the radionuclides and geological materials. Please, you can use this microphone. Okay.
Thank you. Good afternoon, auditory. Let me introduce you to my cooperation with CICRR facility and the group of Dr. Lorinčík from Research Center Rzesz. Let me introduce you to the topic. I'm a geologist. I'm working with the group of radiochemistry at the Academy of Sciences. However, I deal mostly with geological processes and geochemistry. So the connection between geology and nuclear technologies is, of course, obvious because the radioactive substances and nuclear fuel comes from the Earth, of course. It's a notoriously well-known pitch blende, uraninite, as you know. I don't know how to point it. Never mind. This one. It is more than 100 years ago the first radiochemists has extracted the new metals and discovered radioactivity. From those times, we have a great inventory of various nuclear products because of both civil and military activities, and the most, as previous colleagues referred, the most applicable, or let's say most observed and intended way of nuclear waste storage is underground repository, long-term underground repositories. So considering the age, how long it has to decay in a safe place. So geology can help some way, and we can study some natural analogues from nature, minerals and substances that contain uranium, and we are able to date them. So we see the processes around the uranium-bearing substances or radionuclide-bearing substances. Okay, so next. My field of study was always radiation damage, or my favorite one. And on this picture is shown a micrograin of mineral zircon, what is zirconium silicate, that accumulates some amounts of thorium and uranium, and the halo around, it's the result of alpha particles that are bombarding during the time scale of hundreds of millions of years. It's bombarding the mineral around, in this case biotite, what is kind of mica, a glittery one from granite. And it changes its physical, optical properties, and of course chemical properties. So this is the good example how it works, that the material is influenced by the radiation, the heavy ions of helium, energetic ions in MeV units, like around 5, let's say 5 mega electron volts. So its range is in some tens of microns. In this case, it's about 20 microns, and we need microanalytical tools to study this. So I'm working with the group of neutron activation, and we don't have any microscopy, but there is always some possibility, of course, because if I need at least some basic electron microscopy, I could find it in CICRR, in research center, applying for open access project to support my study. And here we go. Let me introduce you what we have studied. Oh, firstly, this is the microscopy facility, microscopy laboratory with LIRA-3 machine that have many options, many possibilities. We have used only some basic modes like secondary electrons, backscattered secondary electrons imaging, and EDX analysis. And first kind of material we've been studying, it is very old fossil resin that was found in uranium-bearing sediments of Hammer, that is close to Stráž pod Ralskem in northern Bohemia. It comes from drill core, and the drill core is very rich in uranium. Formerly it was mined as uranium ore. So we found that these pieces of amber, let's say amber or resinite, has inclusions and very thin microscopic veinlets of uranium. It is disseminated, and there are some features that are very similar to the ones you have seen in mica. So we suspected this might be action of the alpha particles, and so we have chosen some part with these patterns, and then observe it, measure it, and have found that there are some chemical changes in the halo around. It's a sulfur enrichment. We did it using line scan, and all the data shows very similar values of the range, like alpha particles should have in this kind of material. So we compared it with simulation, numerical simulation, using stream code and other codes, and we really got the same or nearly the same pattern as we find in nature. So let's see it from closer distance, and you clearly see the halos. And those halos are studied by other microanalytical tools, and the overall changes in this material we studied by spectroscopy, infrared, and so, but it's not part of this presentation. I just focus on the microscopy at the CICR. The next one is material that is that might be really considered as natural analog, because this is oil-derived bituminous substance that is called anthraxolite, and it is exposed in the northern Bohemia, close to Krkonoše, and it contains at some parts it contains really a lot of uranium, like up to 5%, 8% of uranium, so it should be considered as an ore. How it works? So here you see the black one. The black one is bitumen or pyrobitumen, let's say. It's insoluble. And it contains a lot of uranium in a form of small grains, like detrital grains. And we see that it is placed in kind of fault structure, tectonic structure, where some movements was before, they are traceable by some structures, and we also see red zones that are showing oxidation zones, where meteoric water get and then interacted with this material. So if we take a closer look, we see uraninite grains embedded in the bitumen, and we know that these grains of uraninite are at least 250 million years old. And what is remarkable that the parts where there are not big contraction cracks from or mechanical cracks from tectonic movement or pressure changes, this uranium material is only migrating in very limited scale. Firstly, we thought that might be that this halo around, might be a kind of alpha particle range, but it seems too small, too short, and we really found that it's only diffusion of uranium particles, uraninite particles, uranium compounds that was retarded and enveloped in the bitumen during its maturation. So now you can see how natural bitumen can be useful or powerful when you need to retard, to stop some or isolate some products from migration, let's say migration. So we used a method of elemental imaging, elemental mapping. As you can see, this is the uranium around, only diffusional halo, and only in few cracks you see some foreign elements that has migrated. So this method is really good to continue in looking for migration of some fluids and some salts and products of weathering of this material. This is another method we used also to check by line scanning, to check the elemental composition. This looks like kind of broken piece of uraninite grain, and we have not found any changes similar to previous material. Okay, you see the power of this method. You can choose any area, then you, for example, suspect there is a veinlet that served as a migration path, and then we can check what elements were mobilized and reacted together to create the new phases that has precipitated. And you can do it also in several modes. You can RGB combine various elements to see that, for example, this line in the corner is not only artifact of electron optics, a mere crack, but it's filled with something. So we can find it's filled by arsenic, uranium, arsenic and uranium compounds. So probably uranium was migrating and immobilized by reaction with arsenides, as we found further. So we can study also morphology of those things we have seen in 2D. So these are uranium minerals. The first one that on the left, it is suspected rasfordine, that is carbonate of uranyl carbonate. But this method do not allow us to say it clearly, but we suspect it. On the right, it is nickel, uranyl arsenate called metarauchite, and it is insoluble compound. So it was formed after precipitation of uranium with arsenates. Arsenates are coming from dissolution of arsenopyrite and arsenides of nickel and other elements. And once more, to compare the SE mode and BSE mode, as you can see, heavy particles that contain uranium are nucleated on the substrate of the anabergite crystals. Anabergite is the copper arsenate, and let's say this is what I wanted to show you, what the beautiful possibilities I got here, and what the beautiful data we got from this research, and we published it, of course, because we want to share our findings, and so we attended some international conferences and made some publications. Another one is in preparation. So once more, I want to thank you a lot for this opportunity. I'm thankful to the Center of Research in Rzesz, Research Center Rzesz, and CICRR project, before SUSAN project, that have helped me to get my data and material for publications and dissertation. So thank you. If you want, you might ask me.
Thank you very much, Vladimir, for your presentation. I would like to ask if there is some question from the audience. No? We are really glad that you presented the research which you were doing also together with our colleagues, and also you mentioned here very well the project which is going to be presented next, but there is still one question.
Thank you for the presentation. Are the results somewhat applicable, or the knowledge transferable to the deep geological repository, and like the potential migration and behavior there?
Yes, I think so, but it's a question for the engineers, because they have their directions of research and technological solutions. And this might be inspirational for them. Of course, there are some concepts of bituminization of nuclear waste. So that is why this might be considered as natural analog. There are some proposals of immobilization of nuclear wastes in synthetic hydrocarbon polymers. So this might be also something that might be inspiring for in the field of creating new combinations or new kinds of matrices to immobilize some kinds of waste. And of course, the solubility and pathways of uranium species and the precipitating of new phases might be also a kind of analogy for someone who try to project how, in the worst case scenario, how the aqueous solutions released from such a repository might behave in contact with rocks. So probably it is applicable somehow, but it is a question for engineers.
Okay, thanks once more. Thank you very much. And as you see on the slide, mentioning the infrastructure, large research infrastructure is coming. The next speaker who is going to tell you more about that. Soon. I find the presentation, sorry for that, at the last moment. Yes, so, Jan, you already heard this morning our welcome speech. So, as I already mentioned, he's going to tell you about CICR. So, the floor is yours.
Good afternoon, ladies and gentlemen. I'm going to present something a little bit different than the previous speakers and other speakers. My presentation is not about research results. It's about the place where the magic is happening, what are the conditions to use it, and what is capable to be done. In General Czech Republic, we have specific approach to research infrastructures, especially under the Ministry of Education, Young and Sports. There is a way how you can get your equipment to be, how to call it, large research infrastructure, and to be part of a national list of infrastructures, to get some, let's call it even a money support to run it. But the way how to do that is that you need to be really unique, you need to be really, how to call it, open, you need to do some high financial and technological, you should be on the top. Where to find it? There is a link. Our research infrastructure is not the only one in Czech Republic. There are many infrastructures. They are listed in different topics. We are part of the infrastructure list of energy, but there are others. And in the past, there used to be few infrastructures in our company. Firstly, since I think 2010, we started with infrastructure reactor Řeš, technically means those reactors which are now in our operation. When we get the part of Žilhorovic reactor consortia, so we started infrastructure Žilhorovic reactor CZ. Then there was some note in previous speech about the sustainable energy infrastructure. And a few years ago, there was a decision made to merge all of these three into one, let's like a CICR. It is merged infrastructure, so used to be three of them, now is one, which are based on two we call it large infrastructures, these reactors and the Žilhorovec. In the past, there used to be also Susen, which was then not accepted by ministry, but still, I think it's a really important part because in the sustainable energy project, we built hot cells, loops, and other facilities which are supporting the reactor operation. So the idea was quite simple. Let's take 2 reactors, add hot cells, add loops, add microscopes, add irradiation facilities, different neutron sources, and let's go to the ministry to tell them that we have a large infrastructure called Czech International Center of Research Reactors. Well, I will go back. In those times it was accepted, so the link is that we have now a project for another 2 years, which means that we can get users, we can provide access. One of the key aspects of large infrastructure is that the infrastructure should be offered, we call it open access mode, which means it's not really free of charge, but it's close to it. But that means it should be open for researchers for different topics. These topics should be assessed, financially assessed as a possible, assessed as a cope with the infrastructure, and then done on the research infrastructure. In our case, we are doing it in the form that we usually announce, we call it the calls for open access approach. So these calls are then listed on our website, and people can apply for different infrastructure devices or equipment which is part of this infrastructure. There is usually a big, like a question, who can be the user? On general level, we said that the user can be individuals, teams, or even institution, but this is the main part, it's an academic sphere, even the business, even the industry, or even public services, especially from European research area, but also other researchers, so we have other accesses even from the whole world. These people can be researchers, can be students, can be technical staffs, which are doing some kind of research, and they require some kind of equipment which is necessary for their research, and they are not capable to get finance to directly pay for it. But the main idea is that these accesses should be almost free of charge, because normally you are not going to pay for classical work, only if something specific needed. But the outputs have to be publicly accessible. That means you cannot do something like I'm going to measure something and then sold it to someone else. No, these results have to be published openly, which is a big, how to say, big condition. That means we need to prove that these money are not affecting some kind of disbalances on the market. So it's free of charge, but the results are public. Our technologies are selected like 2 reactors, experimental loops, hot cells, and other laboratories, and my presentation will be mainly as a basic introduction to those places, because for tomorrow we are preparing a visit day, so if you want, you can go with us, or please go to the link of our website. You will see a description of these facilities, and of course there is some kind of context, so you can ask these. For each, let's call it technology, we have something like a technology manager, so you can speak or write with those to share what is possible to be done, what is not possible to be done, what is the suitable time, what is the project proposal to prepare it to be more feasible, let's call it this way. Our reactor, from those who are from our company, it's like I think you've been there, LBR-15, a multi-purpose reactor, 10 megawatt power. Technically, it's working like a big source of neutrons, which can be used for different applications. Listed as a material research means that we are doing irradiation of different samples. Then these samples can be sent to different places like hot cells or laboratories when some, how to call it, change on the behavior or characteristics of the materials can be tested. This means material research. Second one, what we are using it is the production and development of radiopharmaceuticals and technical isotopes. Of course, we can produce isotopes on our reactor. In some cases, the development from the past leads to the fact that we are now like a 15% of the world annual consumption of Moly-99 is coming from us. But the development was quite many years from past. Nowadays we have partners to develop methods for terbium-161. Then there is still research for holmium-166. There is now testing for iodine-131 production. So there are different ways what to do. And even there are some open access projects how to get better results from those irradiations. Also, we are doing irradiation for qualification, means we are testing different equipment, mainly neutron chambers, other, to call it INC systems, if they are capable to work under irradiation stress. And the last point is basic research on mainly the horizontal channels, which was technically like, there is a presentation from my previous speaker, but there will be another presentation regarding, for example, neutron tomography, which is happening on these channels. Second reactor is LR0. Usually we've been asked why you have two reactors on the same site. Reason is quite simple. This reactor has an absolutely different purpose. It's not a source of neutrons. It can be, but it is not a source. It is a light water, zero power reactor. And the main characteristics is that if you see those pictures, there are two absolutely different core designs in the reactor. And there are many others. Technically, from the history point of view, we have more than 600 different core designs in our reactor already tested. So it's possible to build whatever you, and if we have these, how to say, fuel and other things, we can build different things for you as a user. So there are configurations simulating autopaths of the VVR1000 reactor to help measure the outage spectra of neutrons which are affecting the residual lifetime of the vessel. The second picture from right bottom, we call it a benchmark position, which means this is well-described neutron field, and inside the neutron field we can put different materials and test the reaction rates and nuclear data like a validation experiment. All of this is done because we have extremely low burn-up, really well described geometry. So all of these things can be easy to measure, easy to describe in the validation code. And that means we can provide benchmarks for testing the neutron codes, testing the nuclear data. And what is perfect, it is still a light water reactor, but we can put there a very different amount of materials and very specific ones like a graphite, fluoride salts. There used to be lead insertions. There was even a sand in the reactor, but it was specific. And there are still, for example, plans to utilize a heated core with 700 degrees C for melted fluoride salts. Experimental loops, I think there is description of the loop. Take it as a circuit. And inside the circuit, we have different media on different parameters. And these loops can work as a different source of data. Mechanical thermohydraulic studies, corrosion studies, behavior of the whole media itself, how to clean it, how to keep it fine, and corrosion stress on the different materials in different conditions. So nowadays, what we have, it's like a supercritical water loop, which is like up to supercritical parameters. There is still possibility to get even to ultracritical parameters out of pile. We have helium loops. There are a few of them, but technically means that these are now ready to go up to 850 degrees C, and we are still now planning to reach 1000 for the next year. We have supercritical CO2 loop. This is mainly for testing different heat exchangers and using the CO2 as a coolant. There is a laboratory for metal liquid loops like lead, lithium, lead bismuth, which are for these fast reactors or for fusion applications. As flywheel loop, it means that there was a testing of corrosion capabilities of lithium fluoride, beryllium fluoride, and other salt, which is like a molten salt reactors or high temperature reactors cooled by fluoride salts. And there was a specific one, it's a concentrated solar power loop, which was for testing these capabilities, how to get these heat from the sun and how to get it as a power source. Many times been asked that, okay, reactors, there are few of them still in Europe, it's not a problem. Many times there are some hot cells, things like that, but what is perfect about our infrastructure is that on one side we have reactors, on one side we have hot cells, and we have loops, so all of these things can do like some kind of harm to the material. Then you can transfer it to the hot cell or laboratory to do some tests, but the main results from the research is that you need to usually look on a microstructure and microchemical point of view. That means what's technically happening to the material itself. And this is perfect that part of our infrastructure is this laboratory already mentioned from previous speaker, that we have laboratory for this type of analysis equipped with the microscopes, mass spectrometry, nanoemitters, and many others devices, which can then be utilized for non-active, or some of those are also in the hot cells, which can be working with the highly activated materials. From hot cells, it's also for the tomorrow visit. It is a system of 10 hot cells in our institute. 8 of them is gamma, 2 of them are alpha or meant to be as alpha, with some support as a semi-hot cell. Inside we can have different equipment for different testing, like creep studies. We can bend it, we can cut it, we can put it into different autoclaves, and then prepare samples and go for the microstructure studies. Specific part of our infrastructure is not like just research reactors as a source of the radiation. We put there also our gamma irradiation facility. So we have a cobalt-60 isotopic source. Technically, that's not an issue. So you can find those many places, like in the Rostock, even when they are using it as a sterilization for wood and other equipment. But in our case, the added value is that we can control the temperature of the irradiation. And for example, there was a studies of some electronic parts which should go to the outer space, has been tested there, if they survive or not. Second type of sources, it's our neutron laboratory, which is equipped with the californium-252 source, and also from fusion sources. And then there are many others, like small amber sources. But the main point is that this laboratory is equipped with the different material structures, like what you see is a sphere, as a pure material sphere, and we can study the transport of the neutrons from the sources outside, which is then used for calibration purposes. It is used for evaluation of nuclear data, and again, the californium source is used for neutron fission spectra, and 14 MeV fusion sources for fusion spectra, so we can support both things like fission and fusion research. Technically, there is a lot of, characteristics can be said about all of these devices, about the reactors, about the hot cells. If you want to know more, please go to our website to see what is there. If you are here, please go up. We have a poster session, so we can discuss directly regarding. And of course, because this equipment is capable to do general research, but also a lot of student work. So for students, please come to us and we can discuss possible cooperation, like a bachelor degree, master degree, even doctoral thesis phases, because this equipment is ready to be served for you. Thank you for the attention.
Thank you, Jan. I think that if you have any question, let's keep it to the end of this session, because I would like to continue. Thank you very much for your presentation. I would like to continue actually with the examples of use of our infrastructure. Different laboratories, different scientists, and our next speaker is going to be David Zoll. Maybe I didn't stress enough that our day is divided into two halves, and this half is starting, or this part is starting with the practical use of the CICER infrastructure and so-called open access projects. So I'm very happy to exactly to introduce you our next speaker. So yeah, floor is yours. Thank you.
Thank you. Good evening. My name is David Zoul. I will talk about computed tomography and two projects for which we use this technique. 9 years ago, I designed a gamma tomograph for Research Center Řeš, this one. The device uses radiation emitted by the sample, which is collimated and then detected. The device is designed to image the volume distribution of radioactivity inside small radioactive samples with a diameter of up to tens of millimeters with a resolution better than 1 cubic millimeter. Within the Thatcher and Almara project, the formation of corrosion products from activated metal cores incorporated into fixation matrices at the contact of both materials and the migration of radioactivity in the matrices was studied. For corrosion and interaction experiments, irradiated steel coupons and titanium grade were used. The samples were irradiated at the LVR-15 research reactor of Research Center Řeš. The irradiated metal cores were fixed into the experimental body with a diameter of 50 millimeters and length of 50 millimeters, made of cement of geopolymer. Subsequently, the experimental bodies were immersed in a solution of synthetic granite water in an argon atmosphere and left there for 1 year. After removal from the solution, the bodies were dried, cleaned, labeled, and subjected to gamma spectrometric, dosimetric, and gamma tomographic analysis on an SPECT scanner. In the table, you may compare surface dose rate of steel cores and titan cores. Or estimated activity. You see different between is 2 order of magnitude. The scanning algorithm took 26 hours at a scanning head feed rate of 20 millimeters per minute. The reconstruction of the sample slices was performed using the inverse Fourier transform in the Python code. The result is 20 tomograms of the sample. In the left, you see tomograms of metal, of steel sample. In the red are steel cores, and in the blue are matrices. In the right are titanium cores. By composition of all 20 tomograms in space, the resulting 3D reconstruction of the scanned object was obtained. In figure 8, the detected area of potentially migrating of radioactivity from the steel core into the matrix is marked with dashes. The exact position of the metal cores in the matrix were plotted according to the tomographic images of samples. Standard projection were marked front view, side view, and plan view. The drill bit for ceramics penetrated to all metal cores. The dried material was gradually taken to the marked Eppendorf tubes and subsequently analyzed by gamma spectrometry to determine migration of radioactivity into the matrices. For all analyzed samples, the position and dimensions of the metal cores in the matrix were accurately determined. Destructive analysis confirmed the slight migration of radioactivity into the matrices. A significant milestone in the sensitivity of gamma tomographic scanning was achieved for titanium cores when the imaging was performed using a slit camera, which provides an order of magnitude better signal-to-noise ratio than a classic pinhole camera. In contrast to the compact steel cores, the top, the granular consistency is visible in the reconstructed images of titanium cores down. This is next. This is another experiment. The studied rock sample with natural fracture was taken as a part of project research on fracture connectivity in the underground research laboratory Bukov. The deep repository is planned at the depth of 550 meters, and so the rock samples are taken for this depth for laboratory experiment. The diffusion cell is a device for dynamic transport experiments at low flow rates of tracer through a rock sample with natural fracture. It was registered with the Industrial Property Office as utility model. The experiment studied the possibility of tomographic scanning of samples directly inside the diffusion cell. In addition to the lower risk of contamination of the workplace, this arrangement has significant potential for time-lapse recording of the course of migration of the radioactive tracer through the sample, so-called 4D scanning. Time-lapse recording can provide information about the kinematics of groundwater migration processes in the geological subsoil of sites selected for the construction of a future permanent radioactive waste repository. Measurement of the contribution of distribution of radionuclides using gamma tomography was carried out in September 23 after injection of radioactive cocktail of tracers. The scanning algorithm took 70 hours using a pinhole camera, 3 mm in diameter, and scanning had feed rate of 20 millimeters per minute. In total, a sample area 100 millimeters along the cylinder axis was scanned. Despite the relatively low dose equivalent rate on the sample surface, only 11 microsieverts per hour, the Fourier image of the crack inside was very clear and its position could be determined with an accuracy of 1 millimeter. The reconstruction of the sample slices was performed using the inverse radon transform in the ImageJ software. By composition all 50 tomograms in space, the resulting 3D object was obtained. Inside the analyzed sample, the position, dimensions, and shape of the fracture zone were precisely determined. On the last 12 slices, a branched fracture with absorbed tracer is visible. It extends to a depth of approximately 24 millimeters. Non-destructive 3D imaging of the volume distribution of radioactive tracers in fractures of rock samples allows visualization of sorption positions without the need to destroy the sample. The laboratory study of the migration of radionuclide tracers through conductive fractures in crystalline rock samples allows characterizing migration processes in the rock environment on a real scale in order to evaluation the safety of deep radioactive waste repositories. Gamma tomography opens up new possibilities for non-destructive testing of low activity rock and building materials or other porous samples directly inside the fusion cells. It also offers time-lapse recording of the penetration of the radioactive tracer through the sample. Thank you for your attention.
Thank you, David, very much, and thanks for showing us what is possible to do with gamma tomography. It was very interesting, very nice presentation. So are there questions from the people here in the room? No? There is one, okay. One thing, please, if we can switch to Czech language. Yeah.
Děkujem, Davide. Zajímalo by mě, jestli se to dá uplatnit na ozářené vzorky a jakou aktivitu by ten vzoreček mohl být, abych nezničil ten přístroj.
Na to už se mě ptali na nějaké konferenci. Nejsilnější, co jsme zatím dělali, měl kolem 10 megabecquerel. Takže myslím si, že můžeme jít jako ještě výš, protože máme teďka kvalitní kolimátory, masivní wolfram s třeba jenom milimetrovou pinhole kamerkou, takže můžeme jít do gigabecquerel. A tam je spíš otázka té laboratoře. Pokud to je na volné pracovní ploše, tak si tam nemůžeš dovolit pracovat s nějakou velkou aktivitou. Pokud by to bylo nějaký laborace, která už je jakoby zařízená na takové vysoké aktivity, tak to samozřejmě není problém.
Jedná se o tu kameru, nebo co by trpělo nejvíc?
Nejvíc by trpěl scintillační detektor. Tam je kadmium wolfram oxid a to je jako velmi citlivé zařízení, ale říkám, je tam masivní wolframový kolimátor před ním, takže nevidím problém, jako jít do jednotek gigabecquerelů asi, ale musel by se to zkusit.
Děkuji.
Děkujeme. Já jsem ještě viděla tady ruku zvednutou.
Promiňte, mě uniklo, jaké nejmenší rozlišení, jaké jsou možnosti nejmenší rozlišení?
Zhruba kubický milimetr.
Kubický milimetr. Takže teoreticky by se tím dali studovat nějaké, dejme tomu, hrubozrné sedimenty, které by byly nasycené radionuklidem nebo něco podobného. Děkuji.
Tam je spíš zajímavá ta spodní hranice té aktivity. My jsme, tam to bylo v tom jednom grafu, my jsme dělali vlastně vzorečky, mně už se to nechce pohybovat, ale dělali jsme vzorky, které měly, já už jsem to přeběh, tady. Dělali jsme vzorky, které měly v podstatě 16-20 kilobecquerelů. Jo, takže ta škála je vysoká. Ten slitážní detektor se dá v podstatě používat bez přepínání přes 5-6 řádů. Jo. Takže já, když na něm snížím napětí, tak můžu samozřejmě měřit vzorky s vyšší aktivitou. Obráceně, když napětí zvednu až na 60 kV, tak můžu měřit úplně ty nízoučky aktivity, jako je toto. A použití ještě jako lid kamery vlastně můžu jít ještě níž, protože tam mám širší to okýnko.
Já využiju takové příležitosti, ten dotaz tady padnul. My hrozně rádi jako tou infrastrukturou vyjdeme vstříc uživateli. Jenže máme nějaká třeba státní povolení na to, co smíme dělat, jaká máme povolení na aktivitu a další věci. Není problém experiment jako rozšířit na vyšší aktivitu, ale prostě jsou nějaké limity, kdy můžete dělat s otevřenou aktivitou v volném prostoru. A teď jenom řeknu ta věc, kterou my většinou, jako ta urgence vzniká právě v tom, že pokud máte nápad, že to chcete využít, prosím včas komunikovat skrz ty naše stránky s tím správcem laboratoře, protože ono se dá přizpůsobit kde co, ale ono to chvíli trvá. Vyřídit změnu povolení chvíli trvá. Sehnat lepší stínění chvilku trvá. My hrozně rádi jako vyjdeme vstříc, ale musíme to vidět včas, aby jsme se na to připravili. Čili není problém pracovat s vyšší aktivitou, protože pokud se domluvíme, že na to bude kapacita, tak se na to udělá třeba rukavicák, nebo se na to vezme horká komora, nebo se něco postaví, protože my prostě na volné ploše nemůžeme jít s tou aktivitou zase tak moc vysoko, aby jsme neporušili pravidla práce s tou, jaký máme dneska povolení. Čili formálně jde udělat jako spousta věcí, ale je potřeba respektovat například to, že máme prostě třeba nějaká povolení, byť třeba jenom na to, že se to nezdá, ale i třeba způsob využití jaderných materiálů, který máme na pracovišti. I tam je napsáno, jak se smí využívat, taky si s nimi nemůžeme dovolit úplně cokoliv. A úplně stejně to prostě s nějakou volnou aktivitou, tak aby jsme náhodou neporušili podmínky povolení.
Okay, děkuji. Já děkuji Davidovi. Thank you. It was exception. We continue in English. Our next speaker is created in several languages, so no problem to give it in English. So please, you will come here, Novák, who will tell you something about the measurement of neutron spectra.
Nice to see you all here. Sorry, maybe I will sometimes switch my glasses, one of the 4Ds. Okay, I am, as Jana has said, my name is Novák, and I am, at the present time, I am a head of the department which is called Laboratory Operation. We belong to the section of reactor safety, and our laboratories, which is a couple of rooms, and few people. We are located at the building of the zero power reactor and one of the laboratory also in the LVR-15 reactor. This small presentation will show the example what else or what we can offer the customer or applicants. They are accessing the open access in our company, and our laboratories are equipped with many measurement equipment, as there are neutron spectrometers based on the different detectors, also the high purity germanium detectors and others. In the end of my presentation, we'll see other possibilities, and in this case, as we were invited, and now I am coming to the object. We were invited by the Czech University Faculty of Nuclear Science and Physical Engineering to participate in very interesting project, which was, let's say, dose rate measurement based on the Bonner spectrometer, and our task was verify spectra with our fast neutron spectrometer based on the proportional counters. This experiment was, or the head of this experiment was Professor Miloš Tichý. He's a teacher or professor at the Czech Technical University in Troja, and also our long-term collaborator. And for us was very exceptional because after 50 years, I never had visited such place as a interim storage in the Temelín, and especially in the winter time. It was very interesting to find a nuclear power plant in this winter time, and also was very convenient that if you enter the room with these big containers for spent fuel, you get such wow effect. You are in the middle of the huge castor, huge containers. And what for me was surprising that they have two colors. One of them they were blue and one of the yellow. Blue were from Škoda machinery, produced by Škoda machinery. Yellow are typical castors. And each container contains around 22 tons of the spent fuel. Its information was new for me. Okay, so what we are doing, there is a scale here. I am this one, and this is my colleague, just the older one, Mr. Bohumil Janský. There is a scheme where we measured. Each measurement has been performed among, let's say, four castor containers. One position was among the Škoda containers, one of the castor to compare the spectra behind slab of the material, of the iron material that they are made, the containers are made of. At the beginning, as I mentioned, was in the winter time. This was except the radiation producing by the neutron and gamma radiation producing by the containers was also heat. So it was very convenient to have a natural heating in the hall without any additional possibility except the warm coat. What we were doing there. We had measured spectra, neutron spectra, using our spectrometer. For the people who are involved as electronical engineers, there is a scheme or wiring diagram of this. It contains the hydrogen propulsion detector, which is a small sphere with diameter about 40 millimeters, filled by hydrogen, and the spectra measurement is based on the method called proton recoil method, where the neutrons are entering the nucleus of the hydrogen, giving the energy to the protons, and the protons are ionizing, and the electrons are collected on the anode of the detectors. And then the signal of the detectors come to the charge-sensitive preamplifier. Of course, you have to accelerate the electrons or the ions by high voltage. The two different detectors operate with about 2,000, respectively 3,000 volts of the bias, high voltage, and then after all these signals goes over the analog to digital converter, you get a spectrum. There is On the right side, you see the equipment which is based on the NIM modules at the present time, and this is the part of the infrastructure that was, let's say, lent to the Faculty of Nuclear Engineering. There you see the situation, how does it look like inside. So the ESA, as a colleague Jan Melčák has mentioned, that is necessary to prepare everything. So anytime also we are facing this local situation, local possibilities. So it's a part of the measurement of everything is some improvisation here. So you see the cask for the fluid as a tables, and also is for transport inside the electroplant. The main part of the entering procedure, let's say, is about 60% of all activities we had to be in the heart of the nuclear power plant. So you have to switch the code, you have to measure the activity of all these equipments before measurement. At the left side could be interesting for you. Also you saw on the Jan Melčák presentation is a sphere of the iron with californium source inside, and these two detectors later used for the measurement are calibrating. This is energy calibration, and it is necessary to do before any measurement. Oh, there is I am sitting here. No, it's a little bit really improvising procedure. We are there is a land we cannot cross over, probably of the possible contamination somewhere. The location of the detector was about 1 meter about the floor, about the repository floor, and we measured in one time with the two different detector covering different part of the spectra, with the 4 atmosphere lower part and with 10 atmosphere hydrogen higher part. This is the staff, some of the staffs from the nuclear power plants, and 1 or 2 people from the nuclear energy from Faculty of Nuclear Engineering. What we did, this is the output of our spectrometer. You see here, it is for the people who are not involved in it, it is just line coming down like former friends from institute in Russia, they say, see how beautiful spectrum it is. Yeah, I always, as I was young, I saw always only the lines, but the experts saw the special shapes here and others. So this is the spectrum you see here is called the apparatus spectrum, and should be evaluated as a proton spectrum and should be transferred to the, after some procedures of the, like a deconvolution, to be transferred to the real neutron spectrum. What is interesting here, of course, our laboratory is intent to verify models or calculation prepared using MCMP calculation with the different nuclear data libraries, and we are able to verify by using the integral experiments which nuclear data libraries are the best for the specific solution. So if you see the calculation behind slab or layer of the 25 centimeters or over the 50 centimeters of iron, you see the shape of the spectrum, of the neutron spectrum measured by our spectrometer correspond to this, let's say precisely to the expected spectrum. The result that was later used in the articles, there is a comparison of our two black and red lines. There is a spectrum until 4 MeV. compared with previous measurement in other repository. This blue line was added by the Faculty of Nuclear Engineering. Yeah, there is some. Okay, there is. There is some. Yeah, it's impossible to remove it. Yeah, I like to show you what is the end of the measurement. We had, in collaboration, or Faculty of Nuclear Engineering has published the article, which is called Measurement of Neutron Spectra in Spent Fuel Storage, and it is also the output of the open access for us, so we can refer to these articles to see our names. And 3 people participate from our company. There is a reference. So the authors recommend in this article that is very useful beside the classical dosimetric equipment as is a Bonner sphere spectrometer using also hydrogen proportional counters. So this is for us, let's say. You are very good in it, so we wait for the next time and for other repository. In the end of my presentation, I will show you short promotion of our laboratory. You see already the iron sphere, which is now with californium source inside as a reference standard or reference neutron and gamma field that could be used for the calibration, for the spectrometer calibration, for nuclear data verification, and other purpose. As you see this iron sphere, we have a nickel. We have a heavy water sphere with diameter 50 centimeter, of course, light water and others. Also, we are able to measure the leakage spectra using the californium source at some block of different material. This is the last measurement we finished about 2 weeks ago. This is a Teflon or PTFE. Again, there is a reaction at the floor. Maybe somebody can ask why we use this interesting cone here. This is because all these neutrons react also with the air scattered from the walls, from the floors. So we have to measure 2 times. One measurement is performed without cone, and you get everything. Then you measure with the cone, and if you subtract these 2 values, you will get a pure effect. This is the case with this high purity germanium. This was again in the frame of the open access, which was applied by the Technical University in Ostrava. They were interested in the prompt gamma measurement from the leakage from the iron, polyethylene, heavy water, and other materials. So we had prepared for them the laboratory equipment, and they just brought the high purity germanium detector. We fill it by the liquid hydrogen, and they perform the measurement. To show that we are not only alone and older people here, so we have a young and nice employee or collaborator here. And this is staff from the Ostrava. Maybe some of you are knowing the Michael Košťal and the team of the reactor filling our sphere for the heavy water. Also, what is able to do in our laboratory is measure activity of any neutron sources using is called mangan bus equipment. So the variety or possibility of our laboratory is very wild. Yeah, no wild, maybe wild, not wild. Yeah, wild. I'm a little bit wild. So Again, you are invited, and everybody, of course, also from our company or other listening companies are invited to come, and we are able to prepare any situation, any activity, any experiments. Yeah, there is some promo. Again, it was said by, and this is last. Thank you very much for attention. Hopefully see you again.
Thank you, Evgen, very much for your presentation and introduction to your laboratories. I hope that it was as entertaining as for me, for everybody. Is there any question? If not, I would this time say please keep it for the coffee break, which is following, because then we have another part of our presentation, so we are somehow on time, because now we switch a little bit. So I think we can extend the coffee break for 5 minutes. So
send your question by emails, or you find me on the bike somewhere. Okay.
Okay. Thank you, Evgen. So let's start our next part of our day, a long day of conference. I understand you are also distracted, a lot of talks behind going on, but I would like to bring you back and listen next speaker, who is Jana Natoušková from the Czech Technical University. And yeah, she will tell you about what I learned now, the next experience with open access in CVR.
So good afternoon. I hope you can hear me well. So there are still some people coming from the coffee break, so hopefully they enjoyed their coffee. And unfortunately, I won't show you any results either, but hopefully I will show you something interesting. So I would like to talk about the development and the construction of a new neutron imaging instrument in the Czech Republic, namely at the LVR-15 reactor. So first I will give you a quick introduction to the topic, and then I will talk about the motivation behind the development of a new imaging instrument, and then I will spend most of my talk talking about the instrument itself. So the beamline, the detection system, the shielding, and some other components. And also I will talk about some timeline overview so you get the idea what's behind the development of imaging instrument. So first I realized I don't have a slide about introduction to neutron imaging. So what is neutron imaging? Neutron imaging is a non-destructive method that is used to investigate internal structures of optically opaque objects. You already had a presentation about gamma imaging. Neutron imaging is very similar, just instead of using gammas as primary particles, you use neutrons. Why I don't call it neutron radiography? There are many people, they like to call it neutron radiography. Because neutron radiography is part of neutron imaging, but neutron imaging is not only neutron radiography. There's also neutron tomography, there is stroboscopic imaging, and there are also more advanced methods. So, to give you introduction to why we decided to build a neutron imaging facility at the LVR-15 reactor, because in 2022 we successfully built and commissioned a neutron imaging facility at the very low power research reactor VR1 operated by the Czech Technical University in Prague. And based on that experience, we decided to use an opportunity of unused beam at the LVR-15 reactor and build the neutron imaging instrument there. And this project started as a collaboration between Czech Technical University in Prague, the Helmholtz Zentrum Berlin, and also the FRM2 reactor, which is a technical university in Munich. So, what was the motivation behind the building, let's say, another imaging facility? Well, you can see a few points at the presentation. So one of them was decreasing number of research reactors in Europe. So basically for neutron imaging, as for any other imaging, you need a source of particles. For us, you need source of neutrons. So you need a research reactor or you need a spallation source. And with the decreasing number of research reactors in Europe, it can be quite problematic. One of the examples of recently shut down reactor is the BER-2 reactor, which was in Berlin. So it was directly connected to HZB. That's also one of the reasons why they decided to collaborate with us. Another problem is that there are unexpected shutdowns of the reactor and like extended shutdowns. So the perfect example of that is the FRM2. I don't know if you know the story behind the FRM2 extended shutdown. It's quite long, and the reactor is now not operated for 4 years, I think, and there probably won't be any neutrons for another year or so. And another problem is there is a limited number of imaging instruments. So with BER-2 shutdown, with FRM2 also temporary shutdown, you have the ILL, you have a PSI with high flux, and that's basically it in Europe. You have some lower power facilities, but with like really high quality facilities, you have these few. And the problem is that there is quite high user demand. So these facilities are usually overbooked. There is the statement on the slide says they are overbooked by factor 2. Actually, PSI was overbooked by factor 7 last year. So these were the main reason why we decided to build a neutron imaging beamline at the LVR-15 reactor. And another reason was the LVR-15 reactor was probably one of the last reactors, if not the last reactor in Europe, high power reactors, which didn't have neutron imaging beamline. So you know this because you are currently here, but what is this slide about? Well, this is another part of the motivation. This is very convenient because Czech Republic is in the heart of Europe. So for users, because we plan to have the facility for users, this is very convenient. You can have people from all around Europe coming to your facility. And also the LVR-15 reactor is really close to Prague. So it's very easy to come to Prague and to perform experiments at the facility. So talking about the reactor, you already heard some information about the reactor. You probably know it's operated by Research Center Rzesz. So the CTU is not the operator, and it's a 10 megawatt reactor, which is pretty convenient for us. I started with the development of imaging facility at the 100-watt reactor. So you can compare the power of the reactors, and you can see it's quite a big difference. So I'm going to skip this slide because you probably know all of this. This slide is way more interesting for us now. So the LVR-15 reactor is equipped with 9 horizontal beamlines. And most of the beamlines are already occupied by other external users, if I understand it correctly, in the form of open access. So you can see that the beamlines 3, 4, 6, 8, and 9 are used by Nuclear Physics Institute by the Academy of Sciences. There is also beamline number 2, which is currently used by our colleagues from the Czech Technical University in Prague for neutron diffraction. And you can see that the beamlines 7 and 5 are somewhat blocked with the other instruments. So there is one remaining beamline, and that's the beamline number 1. So we decided as a CTU we will rent this beamline, and rent in quotes because we're renting the beamline in the form of open access. So we applied for long-term open access, and we will use this beamline to build a neutron imaging facility at the horizontal beamline number 1. So our neighbors are actually our colleagues from CTU, which is very convenient. So talking about the instrument itself, here you can see some characteristics of the instrument. So if you talk about neutron imaging, you usually talk about different neutron energies. For us, we will operate the facility at the thermal neutron energy with the collimation ratio around 250, which is quite convenient. It's quite high for this imaging facility, and the maximum thermal neutron flux at the sample position will be around 1 × 10⁷, which is one of the, it's not the highest category, but like the, let's say the medium high category of neutron fluxes for neutron imaging. And you can also see that the field of view, maximal field of view that we will use will be around 20 times 20 centimeters squared. Also, if we talk about spatial resolution, because that's very interesting for everyone who wants to perform experiments, everyone asks about what is your spatial resolution. With current detectors, we will be able to perform experiments with around 30 microns spatial resolution, but I'm also working on a high resolution detector, which should be able to do resolution around 5 microns. So if we look at the facility itself, you can see there are some different main parts of the facility. So if you've ever seen neutron imaging facility, this is very standard parts for neutron imaging facility. You can see there is a beam stopper because it's still an experiment with open beam that is coming directly from the reactor core. So you need to stop your neutron beam at some point. There is a detection system. Obviously there are some like some positions, so like positioning tables, like rotation table, translation tables, and stuff like that. So you can move with your sample, or you can rotate with your sample for tomography. There are also beam limiters. This is very interesting part. You can limit the size of your beam in front of your detector, so the detector doesn't get too activated, or like the different parts of your setup don't get too activated. So you put some absorbers right in front of your detector, so you have the direct beam. This doesn't change the collimation of the beam. This just changes the possibility of activation of the surroundings. We will also have a shutter that's already installed at the reactor, but we also need some collimators and filters for neutron beam, because that's a very important part of every neutron imaging facility. Talking about the beam line, obviously all of the beam lines at the LVR-15 reactor are radio beam lines, so this one is no exception. So the spectrum that we will have at the beam roughly copies the reactor spectrum. So the problem is there is high ratio of fast neutrons and also high ratio of gammas. So we had to make some changes, let's say, to the neutron beam to filter gammas and filter fast neutrons. For that, we will use sapphire filters to filter fast neutrons and a bismuth filter to filter gammas. You can see we will have the ratio of thermal neutrons around 98%, which is very, very, very thermalized neutron spectrum. At the image, you can see that's the neutron spectrum. If you don't know what angstroms are, that's okay. It's just a different way to show you the neutron spectrum. So basically, 1.8 angstrom are thermal neutrons. So you can see we have very thermal neutron spectrum with 1.6 angstrom at the maximum. Here you can see the design of the filters. So you can see we have sapphire filter first, then we have a bismuth filter. Then there is another thing, which is a collimator. The problem with neutrons, as you all well know, they don't have a charge, so it's not easy to collimate neutrons. So how would you collimate neutrons? Well, the answer is you don't, because it's not possible. But with something that we call the collimator, it's also called the aperture. So you can see we have this cone-shaped collimator, let's say. It's made out of lead and borated aluminum. So you only have neutrons that are coming from parallel way. So only the neutrons that are coming from the reactor core that are parallel are coming outside the neutron beam. You can see the smallest opening is 20 millimeters. So that's what creates our collimation ratio, let's say. The shutter is already installed at the reactor, so we didn't have to worry about that. We also want to install a fast shutter, which is basically a really quick shutter that is used to open and close in between images. So it's not for really shutting down the beam, because you wouldn't be able to shut down the beam with just the fast shutter. It's just to open and close the beam really quickly in between the images. For the detection system, we will use standard neutron imaging detection system, which is based on digital imaging method. So it's a combination of a scintillator, mirror, and a camera, plus some optics. For the scintillator screen, we will use lithium-6 scintillators to begin with, and later we also want to add some gadolinium oxysulfides because they provide higher resolution. Currently, we have a few cameras available. These are actually very, very cheap astronomical cameras that you can buy for quite an affordable price, so it's really good for testing the facility. And in the future, of course, we want to add some more expensive, more scientific cameras, so CCD cameras or SCMOS cameras. But for testing the setup, this is quite sufficient. And as I said, I'm working on a high-resolution detector, which should provide the resolution around 5 microns. So the most complicated part about this instrument was to design and build a shielding. Because you can imagine if you perform open beam experiments, it's quite complicated. You need to put a lot of shielding around to protect the area. So you want to protect the people that are going around, you want to protect your facility and stuff like that. So you need to create quite a heavy layer of shielding. And you can see this is photo from above, from like the previous setup. And there are a few problems. So you can see there is a neighboring wall of the neighboring instrument. There is also some manipulation area. There's also a spent fuel storage. So the most complicated setup you can get, you have right here. So we had to deal with several problems, and we had to design really specific shielding to fulfill all the radiation protection requirements, but also to fulfill the requirements of the space and people working around. So here you can see the design or the 3D model of the shielding. We were super lucky because when the Bear 2 reactor got shut down, they got rid of a few instrumental parts and they had blocks of heavy concrete for shielding. That was actually quite new. They built it in 2010 or something like that. So they donated us this blocks of heavy concrete, which we could redesign. So we basically played a Lego with the different pieces of heavy concrete, and we built a labyrinth that has no roof because no other experiments at the reactor have a roof. And it's also 40 centimeters walls of heavy concrete, so you can see the model right on the screen. If we talk about other components for neutron imaging, I already mentioned a beam stopper, so you need to stop your beam, not only the neutrons, but also gammas, because they can be gammas created at your detector, at your sample, or anywhere basically when stuff gets activated, so you need to have a beam stopper. You need to also have some other components, such as positioning tables. So I talked about radiography. For radiography, you can just put the sample next to your detector and create 2D image, and you're done. If you want to perform tomography, you need some positioning tables. So you need to be able to move your sample in the position where you need it. You need to be able to rotate your sample. So you need stuff like that. So we already designed these components to use with the detector system. I also mentioned beam limiters, so it's just to reduce the size of your beam so your components don't get activated. You can also use fly tubes, so we might add them in the future, but for now it's not really necessary because the distance between the shutter and the detector is not that high, so you don't really need fly tube. There won't be that big of a neutron loss. But you also need a control system because you need to be able to control your experiment, and not only the detection system, but also the positioning tables. That is very convenient if you have everything on one computer and if you can control all the different components from one computer. So we will need a control system which will be based on Nichols/Tango. I don't know if you've ever heard of that. This is very convenient. Instrument control system that was created at the FRM2 reactor, and now it's spreading to other imaging facilities because it's very user-friendly. So if you have a user coming to your beam, they can easily control the whole experiment. And we will also have a control hutch directly in the reactor hall. So if I give you a brief overview of the timeline. We started in 2021. I think it was December or something. We first came to the reactor and decided to perform some experiments. So imagine not collimated beam, not filtered beam, we just brought the detection system and performed some first tests. And it was actually quite successful. We were able to create images in a few seconds. So later on, we decided we can build the imaging facility at the LVR-15 reactor, like it would be very interesting for us. So we started negotiations about the possible long-term rental of the beamline number 1 under the scope of the open access. And we signed the contract in 2022 in autumn, I think. So in 2023, we started to design the major components like filters, aperture, detection system, shielding, and stuff like that. And also we got the offer of the donation of shielding blocks from Berlin. This year, we successfully transported the blocks from Berlin to Prague. It's not that easy to transport shielding blocks from, especially Germany, one country to another. But Germany, they like laws and they like to push them onto you. So it was a very complicated process to get an approval for transport of the shielding blocks from Berlin to Prague. But we managed to do that in April. And we also, a few weeks ago, I got information that the shielding was already built. So the shielding is currently built at the reactor hall. We also had the aperture and the filters constructed, so we have them ready. Hopefully they will be placed in the beamline in December. And the detection system is also prepared, so it's standing on my table in my office, ready to be put at the beamline to perform measurements. So we hope for the first test in December 2024, which I just learned it might not be happening, but hopefully it will be January, so we'll see. But what's the most important part? Why we built this facility? Well, we built it to provide open access to users. So it's actually open access in open access, because we are using the infrastructure of the LVR-15 reactor in the form of open access to build the facility, but we will also provide open access to users to use our facility. So but we need to fulfill all the requirements. So if you want to see what's the current status of the facility, you can see that the shielding is built, so it's standing there in the reactor hall. So tomorrow, if you visit the reactor, you can think about me. The shielding is already there, and hopefully in January we will start doing measurements. On the last image, you can also see there is this is the collimator. So you can see that's the aluminum tube, and inside we have the filters and the collimators and stuff like that. So just to summarize really quickly, currently we are working on unfortunately still on the construction of the new imaging beamline, but hopefully soon we will start with the first test. And we got super lucky that we had the collaboration with facilities that are already working in the field of neutron imaging for decades, I would say. So they have a great experience in this field, and they are able to provide some information to us to build this facility. And we were also lucky that we got donated some parts, because this wouldn't be easy without that. So hopefully I forgot to change that. You can see there is summer. So this was the previous hopes were for summer 2024, and it's November, so it didn't happen obviously, but hopefully it will happen in January. And yeah, as I mentioned, we are very grateful to be able to use or have this facility under open access, but we are also very happy to provide open access to users. So if you have any ideas for measurements or experiments or projects or whatever, you can just apply for open access, and we see what we can do for you. So thank you for your attention.
Thank you, Anna, very much for your nice presentation. Is there any question? Is anybody willing to have a neutron image of himself? No, there is one.
Yeah, thank you for the presentation. I'm sorry I missed the beginning, so maybe you already answered my questions, but if I'm not mistaken, you did similar measurements in VR1 reactor, right? So could you compare the capabilities of the VR1 that you did and the future facility that are being built?
So the comparison would be really simple. The VR1 is 100-watt reactor and the LVR15 is the megawatt reactor. So for us, we are able to have a neutron flux at the sample position, because that's the most important parameter. So how many neutrons you have at your sample. We have 10 to the 4 at the VR1 with exposure time around 10 minutes. And it's very grainy and it's very noisy. You can still see image, but it's very noisy. Here at this reactor, we have neutron flux at the sample position around 10 to the 7. So 3 orders of magnitude different. And I still think it's really good to use both. So it's not competition between those two reactors. It's actually very good to have both, because when you have high power, you usually want to perform many experiments and like complicated experiments and stuff like that. But if you don't have time, or you have a company and you don't want to spend money and you want to just perform like test experiments, you can go to the lower power reactor and just do really quick measurements and compare if it's even worthy for you to go to the high power reactor. So it's not a competition.
Small remarks regarding the time. It is just a perfect example. That's always a problem on the reactor. Why? Just for info, the shielding is almost 40 tons heavy. Just for info. That means that firstly we get some basic design. So we take this design, we estimated the weight value, we go for the specialist for statics, because you cannot put 40 tons of material directly on the reactor hull because there are some cavities before. So we calculate it. Okay, they says, okay, it will be working. So he says, okay, bring it. Then during some others, he says, okay, we will slightly change the shape of the shielding. Okay, so you do again the calculation of 40 tons heavy. So this continues till technically last month. So finally we build it, and of course we prepare ourselves for change the filter. But again, when the HFR has been gone, because they stopped the production in last month because there is some failure, so we've been asked to do a campaign, do 4 days off, and restart the reactor again for isotope production. So technically there was absolutely no time to do whatever Jana was promised. So now we're finally looking for end of the year to replace the filter itself. But again, this is the again remark. So if you are planning anything, please come early. We will solve it, but sometimes take a time to do that.
Yeah, good things. We are physicists, so problems are to be solved.
Okay, thank you, Anna, one more time. And here we have our next speaker, honored guest, but online. Never mind, we are happy to see you. He's the professor in the Department of Geological and Mining Engineering of University in Madrid, and also in the same time as the president of the European Education Network. It's Francisco Javier Alorza Tendreiro. Sorry for messing up your name. Hello, can you hear us?
Thank you very much, Jana. It's a real an honor for me to participate in this so nice conference. I have been able to follow a little bit of the conference during the last part of the morning, and now I am going to present my short talk. Thank you very much for the invitation. It's really a pleasure and an honor for me. So I will try to share my wait a moment. Okay, wait a moment if I am going to be able to. Okay, I think that this is much better. Are you able to see my?
Yes. And
Okay,
please put it in the presentation mode because it like this,
Okay.
not yet.
Now
Yes,
it's in presentation mode.
not yet. Now it's
already in presentation or not?
no, not yet.
Not yet. Wait a moment. Because I'm going to do like this. I will see now.
We can see like two slides in one, like, you know, with the slide which will follow. So it's more
Okay.
like your screen. Then, I mean, just to switch the screens.
Okay, but I don't, because the problem is that I have two screens here.
Yeah, that would be the problem. Yeah.
Wait a moment. No, it's not this. I need to go here. Now?
Perfect. Yes.
Okay, perfect.
Thank you.
So sorry by the inconveniences. So I am going to present a little bit how is the situation of the nuclear waste management here in Spain. And as Jana said very correctly, I am full professor in Technical University of Madrid, but at the same time, during these 2 years, I'm going to be the president of the European Nuclear Education Network. Okay, I am going to present first how is the nuclear waste management nowadays in Spain, and after, if I had time, I could go deeper in a more research subjects, but I think that I am not sure that I am going to have time or not. If not, in another occasion, I can introduce to you my research. So in Spain, the radioactive waste management is organized by ENRESA. ENRESA is a national company that was created in 1984 and has the character of a state-owned limited liability company. Its functions are regulated by a royal decree of 2014, and particularly the management of the radioactive waste, including spent fuel, and the dismantling and decommissioning of the nuclear facilities constitutes an essential public service that is reserved to the state, and ENRESA is a technical service of the administration entrusted to render this public service. As you can see in the left part of my slide, ENRESA, in fact, belongs to two ministries, the Ministry of Finance and the Ministry of Science and Innovation. ENRESA has two phases because a part is just an industrial enterprise, but at the same time it belongs to CIEMAT, and CIEMAT is very similar to your center, the Czech Republic, because it's the Center for Energy, Environmental and Technological Research here in Spain. And in fact, ENRESA belongs in the 80% to CIEMAT. But at the same time, this company is controlled by two main institutions. First, the Spanish Nuclear Safety Council, that is the regulator here in Spain, and is the institution that attribute the licensing or the authorization for the different tasks, but at the same time, all the tasks related with the environmental impact that are depending of the Ministry for the Ecological Transition and the Demographic Challenges, the third, that in fact was directed by Teresa Rivera, but the person that now is the Vice President of the European Commission. So ENRESA is really in a very complex situation, having two owners and at the same time needing to give reports and to ask for permit to the regulator and also to the environmental minister. So it's quite complex, but we are already habituated to these things because this was from the beginning of the foundation. In fact, I was working with Enresa from '86, so I have a very long experience with them, and we are already using it, but in any case, I am going to describe. So, in total, the functions are the elaboration of the national inventory, at the same time, the proposal to the Ministry of the National Program, that is the GRWP, and is also the responsible for the management of radioactive waste and spent fuel in Spain. For that, Enresa need to set, design, construct, and operate all the waste management facilities in Spain. At the same time, must organize a safe management of the spent fuel and radioactive waste in its storages and disposal facilities, and at the same time is responsible for the collection, conditioning, and transport of spent fuel and radioactive waste. At the same time, and this is the relation that we have always with Enresa, we are always participating in R&D plans that are directed by them, but are organized with a council of professors and university around that made the proposals that are finally approved by the regulator. At the same time, establish training plans covering the needs for the organization and development of the general radioactive waste plan, and enabling the acquiring, maintenance, and continued development of the necessary knowledge and skills. Is responsible also of the dismantling and decommissioning of the nuclear facilities. In fact, I am now involved in a particular case, and I will show you later. Is also responsible for the financial management of the nuclear waste fund. That is, in fact, the money that we are going to use to make all the operation. And on the other hand, Enresa must also to give the support to the national system of civil protection and security service in the event of a nuclear or radiological emergency. So as you can see, there is a wide number of functions and responsibilities, and for that, Enresa has also only 361 people. So it's a quite big company, but with a lot of responsibilities. It has in total, until now, 5 centers that I am going to describe. And you are going to see that there is many activities and many tasks. So the policy and strategy planning is organized in different and successive general radioactive waste plans that are defined every 4 years here in Spain, and Enresa draws up and submit to the ministry. All this information is evaluated by the ministries and by the regulator, and finally is approved by the cabinet of ministers, and after to upload it to the parliament is finally defined and approved, and is published in the official note of the Spanish state. In this general radioactive waste plan are defined all the strategies, the actions, the technical solutions, the economic and financial arrangement, and also all the scenarios at the short, medium, and long term. In this moment, we are under the 7th general radioactive waste plan, and we have a lot of activities, as you are going to see just now. So the Spanish reference scenario is quite complex. In principle, all the nuclear power plants are going to be closed in between 2027 and 2035. We have already began the dismantling of some nuclear power plants, and the nuclear power plants are dismantled after 3 years of their definitive closure of operation, with the exception of Vandellós 1 that has a serious incident in 1989 and was dismantled during the beginning of this 21st century. We need to continue with the operation of the Cabril disposal facility that is in the southern part of Spain, in Córdoba, that is the diet to very low and low and intermediate level waste, and this facility must be in operation until the dismantling of all the nuclear power plants. We are also working in the action to expand the capacity of the individualized temporary storages that are situated in the different nuclear power plants. We don't have a centralized temporary storage. We have different storages in different plants, and this is also a very complex activity. And another thing that must be considered is the commissioning of the 7 decentralized temporary storages at the different nuclear power plants until their transfer to the definitive disposal, that in principle is going to be a deep geological repository. But in Spain, we are very behind in time of other countries for this deep geological repository. We are just now starting. We have been very active during the 80s and 90s until the beginning of this century, and we have from 20 years now stopped it. For all these actions, this plan has foresee about 20,000 millions of euros that is going to be covered by the fund that is managed by Enresa, and the financial contributions are arriving mainly from the owners of the nuclear facilities. I am going also to talk about that. So this is the nuclear power plant closure plan here in Spain, according to the protocol that has been defined by the ministries, as also approved by the nuclear industry. So as you can see there, the last nuclear power plant is going to be closed in May 2035, after 46.7 years of operation. So the commissioning of all these nuclear power plants will imply the enlarge of the disposal capacity of El Cabril, and also to provide for every site a dry storage able to absorb the capacity of spent fuel in each case. And also, at the same time, we need to start with the deep geological repositories heating and desensing. So we have very long time in front of us. So for the financial system, this is just a short note about that. So the main incomes are from the owners of the nuclear power plants. There are also some part that are becoming from the Juzgado plant, that is the production of nuclear fuel, and also on a small tax that we are paying on in the Spanish. This fund is controlled by the ministers and also for the Court of Accounts of Spain, but Enresa has also the possibility to go to the financial markets and to get some benefits with the financial revenues of this investment. So it's quite complex, but it's a task in itself. So for the El Cabril disposal facility, that is for low and intermediate lower waste, level waste, and also for the very low level waste, we have different facilities. We have in total 2 platforms that are described in the bottom part of my slide. In these times, we have in total 28 bolts, and at this moment, now in this year, we are already at 81% of occupation. For the very low level waste, we have more space. We have until now 2 cells that has been created and operated that are between the 26% and the 29%. And we are constructing the next one, the cell 31 that must be operating next year. And there is another cell that is foresee in total the total volume available would be 130,000 cubic meters. So we have, from this point of view, quite a lot of the space. But for the level and intermediate level, low and intermediate level waste, the situation is not so good. So the management of the spent fuel is at this moment in the pools of the nuclear power plant. We need to transfer that from the pools to a dry storage that is going to be created in every nuclear power plant, and from that is going to finally transferred to the geological disposal around 2070 or 2080, something like that. So the starting point is the removal of the spent fuel from the pools to start the dismantling of the nuclear power plant, and for that we are organizing interim storage facilities at each nuclear power plant. So the decommissioning program until now, we have shut down 3 reactors that are at different stages of the decommissioning. Van der Joos 1 that was stopped in 1988. José Cabrera nuclear power plant, that is in which I am now working, it was shut down in 2006. We have started dismantling in 2010, and we are now in the last steps: remediation of the contaminated areas, site restoration, and all the waste of level low or very low are already transferred to Del Cabril. And now we are starting with the Santa Maria de Garoña nuclear power plant. The preparation was initiated in 2019, and now are in the moment of to start with the preparation of the buildings to receive all the materials that are going to be produced during the dismantling phase. For these 3 cases, we have already an interim storage in dry situation that I am going to show you later. So, as I said, the extension of the Del Cabril disposal facility is already afforded. So the first thing is to create a new platform with much more space for the future waste that are going to arrive from the dismantling. This will be in the southern part of El Cabril. If you can see in the left bottom corner of my slide is the last road, the higher one in blue. This is this platform that is going to be created. So now we are going to start at the beginning of next year the operation and the construction. The operation will be in 28. We are creating the disposal cell 31 for very low, that is already under the supervision of the regulator, and we hope to start to build it in next year. At the same time, we are participating in different R&D projects, sometimes inside the EURA two proposals inside the Sudoku project, and for that we are going to cover a vault in the southern, in the north platform, in the vault number 5, and on that vault we are going to observe what is going to be the evolution of the different thermohydraulic parameters of the vault with time, once that the coverage of this vault has been built and is working. So for the establishing the interim dry storage, these are pictures of the already available dry storages in different power plants, and you can see here a short description of the casks that are going to be used in the different situations. So depending on the kind of foil that we have, and depending on the number of elements that we have defined different casks and different situations, different systems. In fact, you have there that until now we have already loaded 118 casks, and we are constructing several hundred more to have all the things organized. And for the case of the future dismantlings, we are now licensing new casks and new systems, because the previous ones are not completely suitable for that one. So on the other hand, and finally, we are working on the establishment of deep geological repository, following the Spanish concept that was proposed in the 90s and was stopped until now. So in this new general radioactive waste plan is established that the opening of the task is going to be next year, and from that we are going to follow all the stages until normal operation in between 2074 or near the 22nd century. So we have a little bit behind other countries, as you can see here. So at the same time, we need to be extremely patient with the transparency, with information, with the communication. Here in Spain, we have a very high, strong environmental philosophy, so we need to be extremely conscious with these things. So this is the main aspect. I have had many other slides prepared for you, but I think I can stop here, because if not, I'm going to go on the time of other presenters.
Okay, Pachi, thank you very much. Thanks for your presentation. It was really interesting overview you already had here. Something from Czech, something overview from the European perspective, now
yes,
from Spain. So now we have, for me it was very interesting. I even didn't know how many power plants you actually have. So thanks for the presentation, and I will ask if somebody has a question here. If not, thank you very much for your time. You know that you are a busy professor. We are admiring your office, by the way.
Yes,
okay.
Yes, I'm now in my office, but I need to go in another meeting just now. So
okay.
Thank you very much.
Thank you.
Send you the PDF of my presentation, and you can put it in between the participants. And I will be very glad if somebody has any question or commentary to.
Exactly. We will send it to you.
Thank you very much.
Okay. Thank you.
Bye-bye.
Bye. And in the same time, I would like to welcome actually our next speaker. Many of you probably know him from being here in CVR many times, but unfortunately not today. That's very good that you put the program. And the next speaker, Theo, is going to tell about the experiment which are actually currently ongoing together with our colleagues on LVR-15 reactor. So I think, please, if you would like to say a few words about yourself and share your presentation, that would be better. So, floor is yours, Theo. Thank you.
Thank you so much, Jana. Thank you for the invitation, and thank you for having me here, not only for this conference, but also for many experiments and many sessions with all the beloved colleagues over there. We miss you very much. We have completed one group of experiments, but now we're moving on to the new project, to our new project together with you all. I think, okay, I am in Oslo University Hospital, a group leader there, and we came to meet all the people at ZESH through a collaboration for a European project, a Future Emerging Technologies project called FRINGE. And this is what I'm going to talk to you about today. I can try and share my screen if I can. Share. Okay. And can you now see the screen in presentation mode? Jana?
Yes. Thank you very much.
Can.
Yes, very nice.
Okay. So again, thank you for the invitation. And to start talking about the work that we did at ZESH, we need a little bit of introduction into two technologies that already existed: photodynamic therapy of cancer, where you have your cells or your tissue and you inject some photosensitive compound to them, and then after an interval between the drug and light application, you apply light. You have an absorption of the light from the photosensitizer, which goes to the excited singlet ground state. And then it can either come back with fluorescence, or it can inter-system cross into the triplet state, from where it can interact with the molecular oxygen around in the tissue or in the cells. And it can provide reactive oxygen species either by type 1 mechanism, which is charge transfer, or it can provide singlet oxygen, which is the main mechanism of PDT. And then after that, you have the death of cells or the cancerous tissues because of the specific application of light. And then this probably you all know about. I borrowed this slide so it has some sound effects. Don't be scared. So boron neutron capture is based on the specific accumulation of boron in the cancer cells, and then the neutrons come along and they interact, they are captured by the boron, and they break it up into lithium-7 and an alpha particle, and the alpha particle is the one that does the damage here. What are the main disadvantages of neutron boron capture therapy up to now? As our sub-member, scientific advisory board member for FRINGE, Professor John Kalefes-Ras said, the BNCT success at Brookhaven was, for example, was hampered by the fact that following the initial success in rodents, the people involved in the trials tried to rush the treatment into humans, and this failed because the boron compounds that were used at the time, they were freely diffusible. They were not accumulating very specifically in the cancer, and they could not achieve this kind of localization. Please mark that, because I think this is the main thing that we have to offer here. And this shortcoming was the main problem of the failure of the treatment that led to the downfall or decline of BNCT. In FRINGE, in our technology, we use a combination of not boron, but the gadolinium-7, which 157, which is another compound used in neutron capture. And we expect the photosensitizer to accumulate very specifically in the cancer lesions and have a better luck than these early boron vehicles. And the principle of FRINGE is the interaction of neutrons with a gadolinium bearing photosensitizer, which will hopefully both cause the radiological death through capture, but also will help dissipate the energy of the chelated gadolinium into the porphyrin, so it can cause death in a similar way as photodynamic therapy. So just a little bit of a summary here of the mechanisms of interaction of neutrons with gadolinium. It can be either an elastic scattering when there is a recoil of the neutron, and there can be inelastic scattering where the neutron goes at another way, and for the conservation of momentum we have emission at this angle. And the neutron capture reaction, which we hope that is our main mechanism, yet we don't know, which gives out several things like Auger electrons, X-rays, gammas, internal conversion electrons, and so on. We can also consider deep inelastic scattering. We haven't done in our current thought process and analysis. Fringe was a project, I would say, pulled back from the edge of the abyss. The project was supposed to be run at the GEEP-2 reactor of our partner IFE at Norway, very close to our biology labs at the west, about half an hour by car. The reactor, which was the last research reactor in Norway, was shut down permanently a few days before the Fringe kickoff. So we had it in the beginning of May. At the end of April, we had the announcement. The PI of the, I'm sorry for this misspelling here, I meant Czech, like in Czech Republic, of the Czech chemistry team at UCT, died suddenly about 1 month from the kickoff. The coronavirus came just after 10 months from the Fringe kickoff and lasted for 1.5 years almost. And 2 chemistry labs in this process were burned and totaled during the project duration. It feels like a bit of an unnatural coincidence of events. So we had to identify a new venue for the project, given that the neutron sources in Europe are limited, as some previous speakers, and maybe Jan Honza-Milchak said before, allowed only, let's say, 4 to 8 days a year, and that was after a successful application with low chances, and that was an impossible task for our biological experiments. So we came into connection, thanks to also our colleagues from Demokritos and Ion Stamatelatos, and where we could run for 10 days at a time, almost in every cycle of the reactor. But we had to, in the process, create biological facilities in the reactor for cells and animals. Remember, most of the nuclear reactors are physics physics buildings, and they're built for physics and not for biology. So we had to take the appropriate steps to adopt some of the parts of the reactor, or even the reactor hull, into a biological facility or biologically compatible facility. We had to find partners for maintaining cells and animals and providing for the experiments, which were from the Charles University First Faculty of Medicine, and Milan Jakubek, who was also involved in Fringe, and Victor Sikora helped us very much with that. And then in the process of preparing the reactor for biological experiments, we had to get accreditation, of course, for the reactor for hosting animals. So, and there we were. We started working at Cerveger. The first cell experiments were in March 2022. we started the first experiments in a small chemistry lab within the reactor, but then we were offered in the course of experiments a lab which was Lab 119 in building 271 before 223, or in between 22 and 23, something like that, if I remember correctly. But after 2023, when we started installing our equipment there, the lab now looks something like that, and it's a lab which can accommodate biological work, both on animals and cells. And here are some of our colleagues who are working in the lab. This here in the middle, you can see how we position the cells in the port of HK1, and we have the gold foils to measure the flux that our cells received. And then we had equipment like this Bionoi absorber down here, which was a portable absorbance meter for the survival. And then for the sake of the animals experiments, you can see here some shots. Here is a portable anesthesia machine, because the animals had to be anesthetized because they were placed into the port of HK1. And of course, they had to be we had to administer to them the drugs beforehand. We also had some controls, and we could monitor the whole process from with the use of a camera in the small hut next to HK1. And you can see here that we used this kind of a stand or a collimator, let's say, which was around made of boronated paraffin, or was it paraffin, or yeah, I think it was boronated paraffin, if I'm not wrong. My colleagues over there can correct me in that. And it started out from it could host 2 mice, and it started out from a 3 centimeter hole at the back to 1 centimeter hole where we placed the cancer, the tumor of the mouse. And here it is, as it began. It was constructed at the beginning. The mouse was placed here, and we tried to put the tumor, this red dot, exactly in place so it could we could minimize the neutron dose to the mouse body. And from the back, which was inserted into the HK1 port, the neutrons came. Now for the outlook, this exercise of fringe, which was just an assembly of catastrophic events, which turned out to be a success story at the end, helped us bring together a formidable working team, interdisciplinary from all backgrounds and different backgrounds and different disciplines of science. We created a biological hub for the future for both cells and animals, including accrediting the reactor space. And this led to the inclusion of Seveger and the first faculty of medicine in Charles University as partners in a new and ambitious Pathfinder project, which is ongoing now. And it's called New Capture. It's all about the neutron and proton capture. The neutron experiments, both cell and animal, are going to be done in Seveger. And with this, I would like to conclude, and I would like to say to you, watch this space. We're coming back, and we'll be very glad to be coming back and to meet you all again, and to have not only productive work, but also a wonderful time. Thank you for your attention, and I'm now ready for your questions, if you have any.
Thank you, Theo. Thanks a lot for your presentation. Very nice. No drastic picture, so only drawing.
Yeah.
Thank you for that.
Yeah.
I was expecting what we are going to see. Okay. Are there some questions here? It's like the morning, evening, you know, colleagues are getting tired. But maybe they will keep their question when you come back. They will ask you personally.
I think I can see Jan standing at the back. Maybe he has a question. Jan, Honza? Yes, question. Hello. And yeah.
It's like there was a simple question because we tested mice, and there will be probably an presentation regarding the bigger animals and other development. So question was maybe more appropriate for the second presenter. Otherwise, if you can tell us, or what we discussed in the past, what are the plans for the future, like big animals, things like that.
Yeah. Okay. Thank you, Honza. I think the plans for the future is again mice for the next project. It's very nice to have big animals. We want to go into this in the sense of a different approach. For example, in this case, as you saw, we had what we call heterotopic xenograft tumors. Means that they were not, although they're brain tumors, they were implanted in the back of the mice. But if for larger animals, like for example rats in the future, we would like to consider the possibility to irradiate in the brain orthotopically tumors which grow in the brain.
Oh, okay, thank you very much. Thanks a lot one more time. And now we give the floor to your colleague.
Kostas.
Okay, thank you. Theo.
I must, before I leave, I would say that thank you. We had a wonderful time with both Kostas and all the colleagues in such a very nice hospitality and accommodation from all the people in 271 and the reactor, and we miss all the colleagues. I would like to start naming them, but you know, there's so many, and I'm afraid I miss someone out. But we thank them from the bottom of our heart, and now we feel like we are a part of CVG there, and we look forward to our next visit. Thank you.
Okay, thank you. And now the next presentation is also online. As I already said, is the colleague of Theo. It's Konstantinos Leonidas Stephanopoulos from National Center for Scientific Research, Demokritos. So, Kostas, please, are you with us? Could you?
Yes. Hello, Jana.
Nice. Great.
Thank you for the invitation. And it's a great pleasure for me to participate in the core conference. I will try now to share my desktop. I'm afraid that I cannot share it. Yeah.
Something is coming. Yeah. Okay.
Can you see now?
Perfect. Perfect. It's presentation mode. Okay.
Okay.
Welcome.
Thanks again for this invitation. So I'm going to present some neutron simulations for fringe biomedical sample irradiations. So just a a brief introduction. I'm coming from National Center for Scientific Research, Democritos. It's the largest scientific center in Greece. It consists of 5 research institutes, and the personnel is about 1,000 people. I'm coming from the Institute of Nanoscience and Nanotechnology, but the Fringe is a collaboration of 3 institutes, the Nuclear and Radiological Science, where Dr. Samatelatos is research director there, and also from Nuclear Physics Department, where Tandem Accelerator is located. Actually, there is an experimental reactor, but it's not in operation. And Democritos is located at the suburb of Athens, Agia Paraskevi, which is not very far from the city center. It's around 8 to 10 kilometers. As I mentioned, there is a tandem accelerator where neutron beams can be produced. So our first Fringe experiments took place in tandem accelerator. And as Theo mentioned, the Fringe summary is to irradiate with neutrons photosensitizers containing gadolinium in order to detect fluorescence emission and the production of singlet oxygen and reactive oxygen species, which cause death of cancer cells. On the other hand, if we are in the energy of thermal neutrons, we can have a synergy effect with gadolinium neutron capsule theory. So gadolinium-157 has one of the largest neutron capsule cross sections, around 260 kilobarns. And during the capsule reaction, it released energy about 8 MeV. 90% of this energy are gamma rays with a mean energy of 2.4 MeV, and 1% is internal conversion electrons with mean energy 66.5 keV, and consequently X-rays and Dozer-Koster-Kronig electrons with energy about 1 keV. And these electrons are important because they cause the DNA damage resulting in the cell death. So a significant part of our experiments, as Theo mentioned, carried out at LFR 15 reactor, and especially at HK1 beam line. So during my presentation, I will briefly present neutron flux measurements and simulations on solutions and cell cultures. So the neutron, we used a series of foils to measure the neutron flux. We also used gold foils covered with cadmium to estimate the thermal neutron component. And the activities were measured at a high purity germanium detector located at the building of the LVR reactor with the help of Vitek Lupak and Miroslav Vince. So we calculated a flux of around 5 to the 10 to the 7 neutron per centimeter square per second, which is in excellent agreement with the flux measured by the LVR staff. Also, the ratio with and without cadmium was 0.003, resulting in thermal beam. Here is the neutron spectrum from HK1 port provided by Jaroslav Soltes. Except of the thermal part, there is also a significant region of high energy neutrons between 130 and 170 keVs, and a less significant portion of fast neutrons with energy greater than 1 MeV. So we first attempted to measure the flux and the dose within the cuvettes that the experiments with the radiations with the solutions took place. So there is a quartz cuvette, 1 centimeter thickness. So we divided the cuvette in 10 slices, 1 millimeter each, and we filled it with water and 0.1% gadolinium. And we estimated the neutron attenuation about 28%, and the calculated dose was about 0.25 milligrays per second. As a next step, we tried to simulate the cells, the radiation of the cells. So we used this plate for cell irradiation. So the neutrons come from the back, and there is a thin polyethylene, about 180 micrometers, and then the cells are attached at the edge of the plate. So we simulated 20 micrometer thickness of cells, and the rest of the plate is medium and air. We used for the cell monolayer tissue obtained from NIST, and also we filled it with gadolinium. Actually, the simulation takes place at one hole of the plate. So here are the results. At the left figure, we can see the dose from the protons and heavy ions, and on the right figure from photons and electrons. The black color is the cell without gadolinium, and the red with the gadolinium. So in the case of photon and electron, we observed that the gadolinium presence increased the contribution of internal conversion and those electrons by a factor of 10. But there is a significant part of the dose is obtained for impinging neutrons with energy from 1 keV to 150 keV. So as a next step, we applied a microdosimetry model. I'm not going to go through details for a better simulation of the cell lines. Here we used monoenergetic neutrons at various energy, and except the HK1 spectrum, we use the neutral and icon spectra, which are from instruments in PSI in Switzerland. And in this case, the model goes the same, but now for the cell line, we are scoring, we divided the cell line in 2 micrometer diameter spheres, corresponding to the cell nucleus. So these are the neutron spectra from the instruments at Switzerland, where we have carried out some experiments with thermal neutrons as well. So the difference is, we can see that the neutral instrument is a thermal beam, but it has also a contribution of fast neutrons. But the icon instrument is mostly cold neutrons. So the first preliminary results. Here at the left side, we can see that protons are dominant at high energy neutrons, and these are recoils with the hydrogen nuclei. And also at higher energy, we have heavy ions and alphas as well. And the interesting thing is that also in case of thermal neutron beams, like Neutra and HK1, we see the contribution from the fast neutrons with the appearance of the protons. On the other hand, in case of icon instrument, which is mostly called neutrons, we see the presence of electrons, mainly Auxerre and internal conversion. So the concluding remarks, we made calculation for solutions in order to calculate the attenuation and the dose. And also we performed the simulation at, for cell culture irradiations. And we have participated at the Hellenic Nuclear Physics Symposium during 2023. And we have published the result at the HNPS Advances in Nuclear Physics. And we have also participated at the International Conference of Applied Nuclear Physics. And we're now going to submit these results to the journal Application Radiation Isotopes. So this is our team. Dr. Stamatelatos is mainly contributed to the simulations, and Antigone Calamara contributed both to experiments and simulation, and she's also running the Monte Carlo codes. And Dr. Lagogiannis is the research director at the Institute of Nuclear Physics, where the Tandem Accelerator is located. And thank you for your attention.
Thank you very much, Kostas. Thanks for your presentation. Is anybody willing to ask something? Probably very clear presentation. So, yeah, we are looking forward to next collaboration. Thank you very much for your work.
To joining you again, yeah.
Okay. For this moment, we thank you one more time. Okay. Time is running and we are a little bit late, but we still have one more presentation, and I'm glad that Mr. Stepan Jedlan is still with us, and he's going to tell us something about the additive manufactured materials for future. Oh. So. Yeah. Okay. For additively manufactured materials for nuclear reactors. So
hello, everyone. Can you hear me?
Yes, we can.
Thank you.
See your presentation. Not yet in presentation mode, but we can hear you well. Thank you.
Is it in presentation mode now or no?
Not yet.
Oh, wait. Mm-hmm.
Yes.
Okay. So let me introduce myself again.
Not yet.
No?
Maybe one.
Okay. So
you were quick.
Oh.
Try one more time.
Yes. Maybe this one.
Perfect. Thank you.
Okay. So let me go ahead and introduce myself again. My name is Stepan Jedlan, and I'm a fresh graduate at the Department of Nuclear Reactors at CTU in Prague. And I would like to present you my research that I did in collaboration with Research Center Řeš and many other people. And this research is focused on qualification of additive manufacturing methods to fabricate nuclear reactor components, mainly nuclear fuel components. And here's the brief outline of today's presentation. This presentation will be a little bit more technical, and I would like to present you a little bit something about additive manufacturing in general, and then focus it more on the nuclear industry. And then I would go ahead and talk about the methods and materials and the examination that we did with the colleagues from the hot cells department. And yeah, let me go ahead to the additive manufacturing. So based on the few standards that exist on the additive manufacturing, there are basically seven methods. And the first one that is presented here on this slide, the fused deposition modeling, is the pretty much the most common one that I think everyone from you can buy nowadays. It is the most cheapest additive manufacturing technology, and many of you may know, for example, Prusa and others. But this technology specifically is for fabricating plastic objects. But the direct energy deposition and powder bed fusion, those are the technologies that are used in pretty much every sector. For example, the army uses it to fabricate weapons. In the aero industry, it is used to fabricate parts of the engines, as well as in the automotive industry. But for the nuclear power industry, it is a bit harder than that. And that is because in nuclear industry, the safety is supposed to be a number one, or it is a number one thing that is focused on. And that is why the material that is fabricated throughout this artificial method is needed to go through a multiple evaluation of material properties, but not only material properties, but also the printing device verification must be addressed. And basically because the nuclear reactor conditions are very hostile for the material, that means there is a high pressure, high temperature, radiation, and so on. The material needs to be tested at these conditions too. And nowadays, few components have been fabricated and implemented in a real applications, and the main additive technology method for this is the powder bed fusion method. However, we have chosen, or I have chosen the other method that has been presented there, the direct energy deposition, which I will be showing you just in a second. But now I would like to show you a few of the examples that what the additive manufacturing methods, namely the powder bed fusion, can produce for the nuclear industry. And on the left, you can see the pressurized water reactor debris filter, which was developed by Westinghouse, as well as the top and bottom flow plates for the VVR 440 nuclear power plants. And actually, those top and bottom flow plates on the right, they have been implemented on the nuclear on the Ukrainian nuclear power plant sites. And here's the Framatome boiling water reactor lower tie grade for their nuclear fuel, and this lower tie grade was implemented at the Forsmark unit, and the BVR Stronghold AM debris filter, which is also implementation of collaboration Westinghouse and Oak Ridge National Laboratory. This has been implemented to a Oskarshamn and Olkiluoto sites. And now for the experiment itself. So for this experiment, we have chosen the direct energy deposition method, namely the laser direct energy deposition, and we have chosen the stainless steel 316L. And this material was chosen basically because there is a largest group of research done on this material and using the additive manufacturing methods. We also fabricated some conventional blocks, and those conventional and 3D printed blocks were then heat treated together at 1150 degrees Celsius for 3 hours, which at least we thought would result in a recrystallization, but we'll see that in just a second. And on the right side, you may see the LDED technology, which is basically the same as the fused deposition for the plastic, but this one uses wire or powdered material. And as in this case, powdered material comes through the nozzle, the laser goes through a nozzle too and melts the deposited powdered material on the substrate. And then once the first layer is printed, the nozzle goes up and prints another layer. Now the samples, they were obtained through the EDM cutting, and those samples you can see on the right side of the slide. And those samples, there were about 20 from each type of a material, which means horizontal, vertical, 3D printed, and then conventional. And 5 samples of each type of material were put into the LVR15 research reactor on the position H6, which is circled by the red circle on the slide. And we irradiated those samples for about 60 days at 120 to 150 degrees Celsius. And after that, the samples were taken out, and there was a dose measurement. There were a few calculations that we did. Mainly, Jaroslav Šoltes did the calculations for the residual activity and for the axial and radial distribution of neutron flux. And based on these data, we are able to do the calculation and the calculation on residual activity and radiation damage. And now for the tests that we did the tensile test, we did hardness, porosity, then we did light optical microscopy and also the electron microscopy and chemical composition. However, only the tensile test and the electron microscopy were done only on a irradiated material. Nowadays, the nano indentation is going through. We weren't able to do it yet, but now it's going to. Now the measurement is being done, and the tests that we did, mainly the tensile tests that we did them on the room temperature and 300 degrees Celsius conditions, and that was because we wanted to compare them to the literature and to the standards. Now for the results that we obtained at the hardness and porosity before irradiation, as a result of a chosen heat treatment, you can see that the vertical and horizontal 3D printed samples have almost the same hardness, and this hardness is a little bit bigger than the conventional material have. And for the porosity, we are able to get under the 0.1%, which is very good result. And there are few European projects that have the 0.1% as a limit for the porosity. So we also were able to fulfill this limit. Now for the tensile test, that is the most exciting one. As you can see, first thing is that the radiation damage of each type of material is not the same, and that is mainly because of the axial distribution of neutron flux, which resulted in that the conventional material is the most irradiated one, but also there is a result of a radial distribution of neutron flux, and that the conventional material shielded the horizontal 3D printed material. So as a result of those two things, the conventional material was the most irradiated, and however, still we were able to fulfill the standards for the non-irradiated material. And as you can see, as a result of the heat treatment, which I will be talking soon, the LDED vertical and horizontal printed material had the highest strength, but a little bit lower ductility. And for these 300 degrees Celsius tests, the results say that the differences between 3D printed material and the conventional material are more subtle, which is due to the higher test temperature, but still the results are almost the same in the matter that the 3D printed material has higher strength but lower ductility. And here are the results of the electron microscopy, the EBSD that was done, and as you can see, there is partial or there are little areas where the 3D printed material is not completely recrystallized, and also that the grains are a little bit greater than in the case of the 3D printed material. The conventional material is about 5 times, the grains in the conventional material are about 5 times bigger, which resulted in the higher ductility and lower strength of the conventional material. And also you can see that the grains are still a little bit columnar and not equiaxed. And as a conclusion of the measurement that we did, we have found out that the 3D printed material has higher strength and lower ductility, but this is mainly because of the heat treatment that was chosen. But it corresponds to the grain size that we are able to measure throughout the electron microscopy. Also, we are able to compare the results of the laser direct energy deposition to the powder bed fusion, which is the #1 leading technology in nuclear industry fabrication. And those mechanical properties are pretty much the same, but the differences are that the powder bed fusion method is more geometrically accurate when in fabrication of the objects. Now, in the future, we would like to optimize the radiation to obtain the same neutron fluence on each type of sample, and also we would like to address the heat treatment. And at the end, throughout the electron microscopy, namely the EBSD, we were not able to see any objects because the magnification is a little bit too low. So in the future, we'd also like to do the transmission electron microscopy to further address irradiation defects in the 3D printed material and compare it to the conventional one. And this is all from me. I would like to thank the Research Center Řeš and the colleagues for the wonderful experience here, and also the colleagues from Comtes, from the Pilsen, who were able to fabricate the samples for me.
Thank you very much, Stepan, for your nice, clear presentation about the innovative material at the end of our conference. I would like to ask if anyone has a question here. Seems not. So, Stepan, thank you very much.
Thank you very much.
And I would like to thank to all speakers and all of you who attended the conference. We had an overview of presentation from the radio waste management of EU, Spain, Czech Republic, but also how to process, store and stabilize the clear waste, liquid, solid, whatsoever. And in the second part of our conference, we could see several examples of use of our infrastructure, gamma, neutron tomography, material irradiation. You saw for this moment, this metallic material, but also biologic material. I think very broad, and we will continue in this next year. So thank you very much for your attention.